Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is chef is just throwing random words. The problem appeared in October lunchtime and has a difficulty level of easy. The prerequisites for this problem are bitwise operations and math. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the step-by-step detailed approach to the solution. Then, we'll see the pseudo code for the problem, followed by which we will be implementing our code in C++. The problem states that given a sequence of n positive integers a1, a2 up to an, if we consider each of its 2 to the power n subsequences and write down the sum of integers of this subsequence, then what would be the bitwise OR of all the sums that we have calculated? So let's try to understand what this means through a small example. Say there are 3 elements given to us, so n is equals to 3 and the elements given to us are 1, 9 and 8. So how many possible subsequences are possible? So 2 to the power 3, that is 8 subsequences. So we start with the empty subsequence, of course. Then there will be subsequences consisting of single elements, so 1, 9 and 8. Then subsequences consisting of 2 elements each, so 1 comma 9, 1 comma 8 and 9 comma 8. And then there will be a subsequence consisting of all the 3 elements, so 1, 9 and 8. So as you can see over here, we have 8 subsequences in front of us. So first we have to calculate the sum of the elements in each of this subsequence. So this sums to 0, 1, 9, 8, 10, 9, 17 and 18, right? So after writing the sum of each subsequence, we have to then represent them in binary form. So let's see how these numbers will look in binary representation. So the numbers would look something like this in the binary representation. So after writing the binary representation of all these 2 to the power n sums, we have to then take the bitwise OR of all these numbers. So if we take the bitwise OR, the bitwise OR comes out to be 1, 1, 0, 1, 1, which in decimal is nothing but 27, right? So we have to report the number 27 as our answer because initially we had the elements 1, 9, 8. So we found out all its subsequences, found out their sums, represented them in binary and then took the bitwise OR of all these numbers and it comes out to be 27 in decimal. So that is the answer that we have to report. Also, what is this bitwise OR operation? So if we have represented all the numbers in binary as we have done over here, then for a particular bit position, if any of the bit is set, then it will be set in the answer as well. But for this particular position, as you can see that none of the bits is set, that is none of the bits has the value 1. So it will be also be unset in the answer. So that is what precisely bitwise OR operation means. It sees that for a particular positions, if in any of the numbers the bit is set, then it will also be set in the answer or else it will be remaining unset. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. So as we begin with our solution, let's start with making some observations. So the first observation that we make is that although it is given in the question that we have to find 2 to the power n subsequences and then their sums and then find the bitwise OR of all those sums, it is not actually feasible to find all these subsequences. Why? Because it is also mentioned in the constraints that n can range up to 10 to the power 5. So that would mean that at max we have to calculate 2 to the power 10 to the power 5 number of subsequences, which is a very large number. So this is not feasible, and that is the observation we are making at first. Second observation is that the final answer that we are going to get will contain that many number of bits as there are in the binary representation of the maximum possible sum. Why? Because as we are taking bitwise OR of the subsequences, so the final answer would be of the same length as that of the maximum possible sum, right? So what can be the maximum possible sum? Let's say that each of the number is at max 2 to the power 30 as given in the question. Although it is less than 2 to the power 30, for simplicity we'll consider it to be at max 2 to the power 30, and there are n elements. So that means n to the power 5 elements. So if you calculate this number in decimal and then convert it to binary, it contains approximately 47 bits, right? So to be safe, we can say that our answer will contain at max 50 bits in binary representation. Alright, so whatever be the numbers given, we now know that our answer is a 50-bit number in binary. Now we just have to determine that which of these bits are 1 and which of these bits are 0. That is, which of them are set and which of them are unset. So to understand the solution better, let's take an example. So let's say that we have 4 elements with us, A1, A2, A3 and A4, and these are the binary representations for the same. And now we also know that the answer is also some 50-bit number or max 50-bit number, and we just have to now find out that which of these bits are going to be set and which of these bits are going to be unset, right? So first simple observation is that whatever bit is set in the individual number, that bit will definitely be set in the answer as well. So for example, we can see that for this bit position, I'll name the positions over here. So right, so the 0th position we know that for A3 the bit is set. So in answer also the bit will be set. Similarly for position number 2, similarly for position number 4 and so on, the bits will be set. So these we know that are for sure set in our answer. So we need to focus on the other bits that are currently 0 in all the given numbers. So does that mean that it will also remain 0 in the answer? No, it does not mean that. Why? Because when we take subsequences and take their sums, it may happen that the carryover may get propagated to this position, making it as a set bit, right? So let's see how to do that systematically. So if I am focusing on a particular bit, let's say this bit, then what other bits affect the value at this bit? So definitely the bits present to the left do not make any difference in the value of this bit. Why? Because even if we take the subsequences and add those numbers, the carryover from these bits will only propagate to the left. So it won't make any difference at this position, right? So instead, the bits present to the right of the position, that is these bits. So these are the bits that actually make a difference on whether this bit will be set or unset, whether this position will be set or unset. So that is how we are going to approach our solution. For each possible position, we'll see that if that bit is going to be set or unset by having a look at the bits present to its right. So before we begin with our approach, there is a property that is going to help us quite a lot over here. So that property states that if we have a x bit number, so let's say we have a x bit binary number, right? So let's say these are the x bits and we have another x bit binary number. So if we add those two numbers, the answer will either be an x bit number or will be an x plus 1 bit number. Why? Because you can verify for yourself. At max, the x bit number can be made up of completely of ones. So let's say we have a 3-bit number, that is 111 in binary, and we have another 3-bit number which is at max 111. So when we add these numbers, what do we get? So 1 plus 1 is 0, 1, then this is 3. So again, yeah. So we get a 4-bit number, right? So my point being that if we add two x-bit numbers, the resultant is always going to be either an x-bit number or it will be an x plus 1 bit number. It cannot jump to x plus 2 or x plus 3, right? So this property is going to help us a lot in building our solution. So again, if I am focusing on this particular bit, I should only be concerned by the bits present to its right. So what I'll do is that I'll keep taking the prefix sum of this 1-bit number. So uh, I'll just underline these 1-bit numbers. So if I write them separately over here, so they are 0, 0, 1 and 1. So this is a 1-bit number. So what if I keep taking the prefix sums? So 0 sum is 0, then 0 plus 0, the sum again remains 0, then 0 plus 0 plus 1, the sum is 1, and if I add all these numbers, the sum is 1 plus 1, that is 1 0. So what we see is that for some time the sum remained as a 1-bit number and at some point it became a 2-bit number. Why? Because of the property that we just saw of the x bit numbers. So if while taking the prefix sum, at any point, if the sum becomes a 2-bit number, it just means that the bit that I am focusing on will be set in in any one subsequence. Which subsequence? So here we can see that if I try and add all these numbers, so after adding all these numbers, you can see that the carry, that is this particular one, gets propagated to the left to this position, right? So we can say that in the final answer this bit is also going to be set. Similarly, if we are focusing on this bit, let's see how the solution will work out. So if I am focusing on this bit, then the bits that I should be concerned about are the ones present to its right. So if I write them separately, these 3-bit numbers, so they will be 100, 100, 101 and 001. So initially it's a 3-bit number that we know for sure. But what if I add the next number, that is A2 in it? So if we add A2, then these two numbers will get added. And what is their sum? Their sum is nothing but 1,000,000. That is a 4-bit number. So we saw that the carry again got propagated to this position, right? So we can say that this bit is also going to be set in our answer. And if someone asks us that for what subsequence this bit will be set, so we can say that the subsequence consisting of just these two numbers a1 and a2, if we add these two whole numbers, okay, a1 and a2 in binary, then the carry of these two ones will get propagated over here. So we can safely say that there exists a subsequence for which this bit is set in the sum, right? So similarly, if we see for this position, we are concerned about these bits, okay? So what we are doing in our process is that if we are targeting some particular x plus 1th bit, then we see all the possible x bit numbers from the given sequence and we keep taking their prefix sums. So S1, S2, S3 is just the prefix sum of these x bit numbers. Okay. So that is S1 is just the sum of A1, S2 is sum of A1 plus A2, this is A1 plus A2 plus A3, because these sums already contain the sum of the x bit numbers, right? So for example, x plus 1 is somewhere over here, then these are the x plus 1 bits. So I'll take these x bits from my original sequence and keep taking their prefix sum. If at any point my prefix sum becomes of the length x plus 1, that is, if my x plus 1th bit gets set at any intermediate step, that is, let's say at some S4, then I can surely say that for at least one subsequence my bit is getting set. So I can stop my process there, or I can set my x plus 1th bit to 1 and for sure say that there is a subsequence for which this bit is set. But what happens if I take the prefix sum for all the elements and still the sum remains an x bit number? So it means that after adding all these x bit numbers, the sum is still remaining an x bit number. So there is no possible way that the x plus 1th bit will be set. Why? Because the carryover did not propagate to the x plus 1th position. So that is why we can safely say that if after adding all these x bit numbers also, the sum is still an x bit number, so the x plus 1th bit will be remaining unset, or else it will be remaining set. So while implementing, what we are going to do is that we will be having the elements, that is A1, A2, A3 up to AN. So whatever bits are set in these individual numbers, that we are definitely going to set in our answer variable, that is in the answer binary representation, but also we will keep taking the prefix sum, that is A1, A1 plus A2, A1 plus A2 plus A3, and whatever bits are set in this prefix sum, those bits will also be set in our answer, because we just saw that instead of taking randomly the subsequences, if we take the prefix sum in order, it will still tell us whether the particular bit is going to be set or not in the answer variable. Okay, so that's how we are going to implement it. So guys, did you know that CodeChef is doing an awesome job by uploading and taking free live classes on Unacademy and YouTube? Courses like Introduction to C++, Java, Dynamic Programming, Recursion are some of the topics that are being covered in these live classes. Not only that, these classes are being taken by some of the best educators in this competitive programming field who have been to the ICPC World Finals or have been the IOI medalists or have worked in big IT giants like Facebook, Amazon, Google, LinkedIn, etc. So what are you guys waiting for? Download the Unacademy app right now or register yourself on unacademy.com and select your goal as competitive programming to access all this free content. You may also opt to get our paid subscription, that is known as Plus subscription, after which you will be able to access the curated content by the educators, wherein you also get extra support like teaching assistants, practice problems, and live problem discussion. Additionally, don't forget to use my referral code DarshanCool25 to get an instant 10% discount on the Plus subscription. The pseudocode for the problem goes as follows. For each test case, we first input n and then the n elements respectively. Then we initialize two variables, answer and sum, to 0, where the sum represents the prefix sum of the elements. Now, for each element, we do answer or equals to element, because whatever bits are set in the elements should also be set in our answer variable. So after doing that, we increment the prefix sum in the following manner, that is sum plus equals to element, and then again do answer or equals to sum, so that whatever bits are set in the prefix sum are also set in our answer variable. Once this process is done for each and every element, we finally print our answer. The implementation of the C++ code goes as follows. For each test case, we start by taking the input for the number of elements, that is n. Also, we initialize two variables, answer and sum, to 0. Now we have to take input for those n elements. So we write while n minus minus, we input an element So let's say ELEM. After taking the input of the elements, we have to do answer or equals to element. So we do answer or equals to element, then we increment our prefix sum, that is sum plus equals to element, and again we do answer or equals to sum. So what will this do? This will keep taking the input for each element, do its OR with the answer variable, keep incrementing the prefix sum, and again answer or equals to the prefix sum. And once this process is done for all the elements, we can just output answer as our final answer. And that's it. We are done with the code. So let's try and submit this code on CodeChef ID and let's hope for a quick AC. Great, so our solution works. Regarding the time complexity of this code, in each test case, we are just taking the input for the n elements while maintaining a prefix sum and as well as doing the OR with the answer variable. So it is safe to say that the time complexity of this code is big O of n.